Is that how you pronounce the name, right? You okay? Welcome. So I'm Salim Ali. I'm the chair of the department. Thank you so much for joining us. And you're okay with us recording it as well? Yep. All right. Good. All right. So I think we'll get started. You got the recording on? Yeah. Okay. So, greetings everyone, welcome. So this is the first seminar for the semester because we've been having a chair search. And so because of that, we've had 3 candidates coming in the first 3 weeks of the semester at this time. So Guido, you're the first speaker for the actual seminar series for the semester. So welcome. It's a real pleasure to have Professor Guido Cervone, who's the director of the Institute for Computational and Data Sciences and a professor in the College of Earth and Mineral Sciences at Penn State, which is a beautiful building. I've actually visited the building with all the mineral collections on the first floor. And as someone who studies environmental conflicts around mining, it was really quite a treat for me to see all the displays there. Professor Cervone received his PhD in computational science and informatics and MS and BS in computer science in 2000 and in 1998. His expertise is in geoinformatics, machine learning, and he's worked in many parts of the world. He's been an Erskine Fellow at University of Canterbury in New Zealand and also an affiliate professor at the Institute of Santa Anna in Italy. And he's the former president of the Natural Hazard Section of the American Geophysical Union, AGU. So thank you so much, Guido, over to you.
Yeah, thank you very much. Can you see my screen? I look it looks very small.
Yes, we can see it. Yes, thank you.
Oh, you can. Oh, okay, perfect. I will.
We can see it, but yeah, let me see if I can move this thing around so it doesn't look. Yeah, this is a bit odd that we've got this header on the top.
Yeah, it looks a little bit small if I.
Yeah.
Okay. Well, it might be
Yeah, there, oops, sorry. Should I try again and we'll see if I can move this view, maybe the view part, view speaker, immersive. Yeah, you can share again. Let's see if it works.
I'm gonna try again. Is that I have a very large monitor here, and
Okay.
give me just 10 seconds whether or not this. Yeah, I don't think it's gonna work. It's too small. Okay, let me try something here, and it's probably not the
Is
best.
it because of your monitor, you think?
Yeah, I think so. Look, I'm gonna do this.
Okay.
You know,
Yeah, that might be a little better. Okay.
yeah, exactly. I'm very sorry. Oh, okay.
Okay.
I kind of minimize. Yeah, sorry. It's best I can do. I have a very large monitor, so when I share my monitor, it comes very small. Well, thank you. So it is good, right? Good enough?
Yes, yep. Yeah, we have Professor Archer has just joined as well. I did the
Oh.
intro, so we started. Yeah. Okay.
Oh, Christina.
Yeah, it is actually there's a confusion about the timing. We moved it to 12:30 because of there was another and officially in the calendar is 12:30, right? Yeah. So sorry, Guido, there was a confusion whether start time is 12:45 or 12:30. But I think we have people
It's my fault. Yeah.
no, so
It's
we can start. Don't worry.
Guido, I'm so sorry. I should have
Okay.
No, no
introduced
problem.
you.
Absolutely. I will start.
I don't even know how to use it. I mean,
Yeah. So thank you so
Okay.
much for inviting me. Yeah.
All right. Well, it
I
would have been lovely to have you in person,
Yeah.
but we heard about your injury and also we
Yeah.
hope your speedy recovery. So
Yeah,
please go ahead.
Yeah, thank you. And yeah, I mean, I actually gave a talk in your department several years back.
Okay.
And I visited Christina a few times. I was hoping to go get some ice cream at your creamery later, but
Oh, yeah.
will be next time. So,
time.
So I want to talk to you a little bit about, this AI machine learning revolution. Right now, it looks like that almost every work that I review here in geography, in GIS, and beyond, it always uses some form of AI. In fact, this was happened last year. I was at the defense of a student who didn't use AI. My question was, why didn't you? So, it has become, so used in our community that, I mean, it's surprising when people don't use it. So let me see if I can do this. So I'll start, by saying, so I remember when I hear Eric Schmidt saying this, was back in 2003. I was, just about the time that I was ready to wrap up my PhD thesis. And he said that, from the start of civilization until 2003, we collected 5 exabytes of data. And that was an estimate of what was available in the Library of Congress at that time. And then he went ahead to say that, at that time in 2003, we collected that much information in just a few days and in a month maybe. And now, we do this, in less than a day. By the way, if you don't know, Eric Schmidt was the CEO of Google, is the only person in US history, I believe, that became a billionaire on stock options. I don't think anyone else was able to achieve this. And the reason why we collect so much data is because there's enormous progress in cyber infrastructure and also the ability to analyze the data using data mining algorithms. And undoubtedly, the AI, ML, artificial intelligence, and machine learning have been driving this computing revolution also because there are no alternatives. The only thing that we kind of talk about and we invest is quantum computing, but quantum computing is one of those methodologies that first still has to be proven for general purpose. And second, well, I wouldn't claim it's an over the horizon technology as it was a few years ago. I mean, we have proven that quantum computing is plausible, but we are years away before it will become the main form of computing. So AI is the only methodology we have right now for exascale computing. There is nothing else. And the widespread of AI is possible because, well, we have tremendous amount of data, tremendous computing power, the fact that we can very quickly transfer data across our planet. We have algorithms that are very well implemented. You just download them and they usually work off the box. They're easy to use. There are so many success stories. And as I already told you, that's the only way we can do it. And really, if you consider the evolution of science, we really start, with those three figures. This slide was supposed to be animated. So, we start from the left, we have Aristotle. And really starting, it was really the first to start talking about, reasoning, think about, the Aristotelian syllogism. And that was the main driver of science, of reasoning and argumentation for almost 2,000 years until Galileo came around. And especially in Italy, we could credit Galileo from starting the scientific revolution, also because he was one of the first scientists that constructed precise instruments. So now for the first time, we can collect data very precisely, and we can use, those data to formulate theories. Then we have this person on the right. Unfortunately, I never met him. I wish I could. That's Seymour Cray. Seymour Cray was really the one person that envisioned, perhaps, before everyone else, the fact that not only we use computers in order, to analyze data, we can actually use them, to create data, to synthesize data, and to come up with new discoveries in a computing environment. And that is something that, right now is one of the main drivers for science. So for the last 4 decades, we have this computation and data-enabled research. It has been very far-reaching repercussions in the sciences, in the engineering, and also in the humanities. Just before this meeting, I was in another meeting about, AI and design. It has been transformative. And right now, I'm almost ready to claim that if a solution doesn't use AI, it might be lagging behind. And we definitely have seen a shift from algorithm development to data collection. So what does it mean? It means that often just give me the better computer and I will give you a better result. When I was a PhD student and I had a problem, I used to spend time in front of a whiteboard with my advisor. I used to do that with my students until probably about a few years ago. Right now, if one of my students wants to get better results, I usually tell them, collect more data. And so we have really had this paradigm shift from developing the algorithm to just collecting and analyzing data. And this has been possible because of the availability of supercomputer. If you see here on the vertical axis, we have performance. On the horizontal axis, we have time. And don't be fooled, the vertical scale is logarithmic. So, it's a much larger increase that it might look like. And the linearity, of course, is linear in a logarithmic scale, but it's quite there. And what you see, the triangles is the number one supercomputer. The square is the 500 supercomputer, and the green is basically the sum of the top 500 supercomputers. So we have, the most powerful of the supercomputer, the least powerful of the supercomputer, and the sum of them. And as you can see, of course, the most powerful supercomputer tend to have the lion's share of all computing power in the world. There is also, a little bit of prestige that goes into having, the fastest. And then, we do see a little decline, but, we have, this relationship seem to be holding, for at least the last 35 years. Where are they? Well, United States leads the revolution. Here on the left, we have countries by system share. So with US, China, Germany, Japan, France, Italy, and then the others. But then, when we look at the country's performance share, so not just, where the systems are, but how powerful they are, then, the US dominates the global market. We're more than 55% of all computing power, supercomputing power here in this country. So this is, we often talk about the US being a superpower militarily, economically, where it is definitely a superpower in terms of computing. And it is quite an exciting time because, never in our history, in the history of our civilization, we have known so much about the planet. We never had so much access to data and computation. And at the very same time, never our society has been so much at risk. That is because environmental hazards and extreme events, they pose a constant threat, often an unacceptable risk. Think about high dams, nuclear power plants, and all other facility use destruction. It would create damage in billions of dollars and thousands of losses of lives. Also because population that tend to cluster in megacities, and often those megacities are along the coast, which are among the most dangerous places to live in. And those are my research team. The reason why we know so much, that is because of remote sensing that allow us to really see the planet with an unprecedented resolution, both spatial, temporal, and also spectral. We have numerical simulations that help us explain the past and forecast the future. And then also social media. I mean, for the very first time in human history, we have a very comprehensive data set of how people react. Think about, like a hazards, immediately, we have people that, they start writing on their favorite social media, how they're experiencing that event. Remember, during the Boulder flood in 2017, there were so many people that were tweeting at that time. They were using Twitter, and they were saying, "Oh, this is the worst flood ever." I mean, no, it wasn't, but that's how people perceived it, and that's how we need to answer them. And the reason why, we are able to ingest all those data and come up with results is because of geoinformatics. That's my field. Often we refer to geographical information science. I really like to use geoinformatics. It's more of a European term. It didn't really pick up much in the US, but I really think it characterized this idea of using artificial intelligence, machine learning, and a source of all other algorithms in order to study those very hard problems. What I would like to remind everyone, especially the students in the audience, that the rate at which the data being generated, collected, exceeds our ability to analyze them. So if you're a student right now, well, you might have a much more difficult job than, the generation before you and before you and before you, because each one of you will have more data to analyze. Fortunately, there are better algorithms, there are better computers, but the rate at which we ingest the data is just unprecedented. And this is really what I do. Those are my research methods. So my current academic interests, they revolve around, image spectroscopy, often called hyperspectral remote sensing. One of the projects I privilege is target detection. I also use a lot of artificial intelligence and machine learning for environmental forecasting, and here is where my research intersects with one of the Professor Archer. I'm also interested in the ethics and sustainability of AI. We'll see a little bit of this at the end of the talk. I hope that I have enough time. And of course, workforce development. I'm a professor, so I'm here, to help form the next generation scientists. And this is a little bit is a word cloud. What I did, I took the PhD thesis of all my students, my 7 students, and I picked up, I think, the 20 most common words. And here it comes, AI, remote sensing, atmosphere modeling, science, hazards, floods, and so on. These are a little bit, those are the topics that I'm very interested in. Those were not handpicked. It's really, I just run the algorithm, top 20. One note that I made here was a note for me that I want to share with you. I got my PhD in 2005 in AI, artificial intelligence, and machine learning. And I had, those big visions, those big dreams of what AI could be doing. Well, I'm surprised by what I've been able to see in my lifetime, and especially what I've been able to see in the last 5 years. I did not imagine that we would get where we are right now. So this idea that, those algorithms are getting ever more sophisticated and they are helping accelerating science is definitely true. I think is absolutely true, and I think it's happening right now. So let's talk a little bit about remote sensing. So this is a technique, observing the planet at a distance. It's operationally used, and it works well, especially in optimal collection conditions. However, there is an unknown level of uncertainty when we have clouds, when there is smoke, when there are shadows, there are like liquid spills, where there is a mixture of materials in the same pixel. And that's just the state of the science. And most of the algorithms that we use were developed in the 90s. They are very solid physics, mathematics, and statistics. However, they are lagging behind the revolution in AI and machine learning. And I would claim that, probably the most significant error is introduced by the atmosphere. And in remote sensing, the atmosphere is paramount. You're either looking at the atmosphere or you're looking through the atmosphere. So it is one of the most fundamental problems we need to solve. And, this is the only equation I have. This is my favorite equation. I don't know if you have a favorite equation, but you're allowed to have one. And this is really the it talks about the amount of energy of radiance that is measured by a sensor. This case will be on a plane. Is a combination of different things. This is the solar component. Will be this. Is the sun that goes through the atmosphere, tau 1. It hits our target at an angle, and then it goes back up. And goes back up, that's tau 2. It's right here, it's multiplied by everything. So tau 1 atmosphere going down, tau 2 atmosphere going up, is transmission of the atmosphere, I should say, times the reflectance of the object. This is then we have LD, which is in the long wave, and this is just self-emitted radiation that goes into our target, and it only depends on T, on the temperature. This is self-emitted. And then, we have, basically LB, which is, the downwelling energy that, from the atmosphere, it's our target and then back into the sensor. And then, we have background. There would be this part right here where some energy goes. It's a nearby target into the, near that background into the target and back into the instrument. And here the blue are the short wave, red are the long waves. And finally, the last 2 components is basically energy that from the sun goes directly into our target, or is self-emitted energy from the atmosphere into our instrument that never reaches the target. And what we need to do really, the entire project of target detection is to be able to compute either R lambda in the reflective part of the spectrum or epsilon lambda in the emissive part of the spectrum. And that's what I do. I've been doing this for about 20 years, trying to estimate this parameter from this. And generally, no, we do it by analyzing one image at a time. And then there are different methodologies to try to compensate from the atmosphere. And then, because, it's very you have to run an entire radiative transfer model. So it's very time consuming. We usually choose one or a few pixels to characterize the atmosphere. And then that solution is applied to the entire scene. What I'm proposing to do here, that was funded by DARPA, was to simulate millions of scenes at different angles, well, taking into account the angle at which we're observing our target. And then, we find up an artificial intelligence-based solution to learn the atmosphere from the different scene at different angles. And we do this for every single pixel, because now that we have an AI solution, it's very computationally fast. So the way we set up the system, we assume that there is a plane on a circular orbit, and then we have a target which is off-center. So depending where the plane is in this orbit, it will collect it from, let's say, 30 degrees all the way to 90 degrees when it's hovering right on top of it. And then, that's what we get. Here in this image on the vertical axis, we have angles that goes from 30 degrees all the way to 90 degrees. And what we have here is electromagnetic wavelength, basically. Here we are between 7 and 13 microns, so we're looking into the emissive part of the spectrum in the long wave. This looks almost like it's vertical, but it's not. It's just an artifact of the screen. I don't know how it looks on your screen. But the idea is that, this is a simulation of what the instrument on the plane would measure. We take this, we run it through our machine learning model, and we try to estimate the atmospheric component, the transmission, the downwelling, and the upwelling, which is divided into two components. And results, it worked really, really well. It's more robust atmospheric correction. We analyze multiple scenes in pixel, and we improve target detection. When I went back, to our program manager, I said, "Yeah, thank you for showing me that it works, but did it really work?" So you see, my hands were tied. I really had to prove that it was working. And let's see if this is. So I actually got to, oh, sorry, I cannot show them at the same time. But we got to fly a plane with a long wave hyperspectral instrument that was gimbaled. And, this is the optical part of the spectrum. You see, there are clouds, unfortunately, that make things more difficult. And this is our campus. And let me show here. You will see that as the plane is orbiting around campus, it's a different vantage point of view. This is Old Main, where there are all those, paintings that, your department head was talking about, and this is our building. And, this is just a zoom out version to show you the 3D diversity. And while the plane was collecting those data, we were on the ground, putting instruments, this is a little pool full of water. And here we were collecting ground truth with a long wave imager and with a contact spectrometer. And what we're showing you here is this is some form of plastic that we had. And the black line is what we collected in the field. And this one is the reconstruction once we remove the atmosphere for this particular target. There is a little bit of uncertainty here, and that is because of water vapor absorption bands. But for the most part, we are able to very precisely characterize this. And we have done this, from a plane that is flying 10 kilometers above the surface. And I just wanted to tell you that the pixel resolution were just a few centimeters. And when we showed this to our program manager, he told us that this was equivalent to years of hardware development. So the project to DARPA was about $800,000, and we probably saved several $1 million in development for new instruments. So why is this important? Well, observing the planet is only part of the problem. The other part is to actually use models to forecast what will happen in the future, weather forecast. And much of the improvements in weather forecasting over the last 30 years has really been better data simulation, like really having a better state of the atmosphere at the initial conditions. So the early state were mathematical models, there were formal description of the processes, and computer simulations that really what made the forecasting predictable, possible. In the beginning, people were just using weather maps, during Second World War, where the real breakthrough came, after the Second World War when we start using computers in order to simulate the futures. But those early numerical weather prediction models were very expensive and, they were good for large scale planetary level events, but, they were not doing very well for local conditions. And then in the late 20th, all the way to the early 21st centuries, we have increasing computing powers, we have much more complex models, larger data sets, we start increasing our accuracy. We have both global and regional models, we have localized forecasting, and data simulation became even more sophisticated, and they start acquiring old satellite data, weather balloons, and so on in those models. What we have right now is this AI revolutions. We started by using AI for error correction. And think about, a numerical model. It simulates not exactly this planet. It's a planet that follows the same law of physics, but there are many expedients, many simplifications. So there is always a post-processing that needs to be done in order to get a simulation for this computational version of the Earth, which is not exactly the Earth, to bring it back into the physical world. And then, we moved away from that. It worked really well, but we start saying, well, maybe we can use AI for more, like hybrid models, but we actually can replace some of the physics with learned models. So this simulation that is imperfect with many expedients, well, maybe rather than using some equation that we know they do not hold true because, there are too many simplifications, we just try to learn it. And then in some examples of those AI-based systems, we have GraphCast, from Google, we have Forecast from NVIDIA, and Pangu Weather that kind of really started it, the Chinese-based model. Now, the future trend is that, we do even more data integration, but things will just be AI-based. So, we're not even going to run a physical model. Originally, this was thought not to be able to work, and then when it was shown to be working, only to work in the vanilla case. And right now, we have improved extreme weather prediction. We have some unified global models, and then really very fine scale micro forecasting. They seem to be the trends in weather forecasting and AI. This is really state of the science. This is work that I've been doing with one of my colleagues here at Penn State. Where it's called GraphCast, where we are actually using, very simple computational resources, something that we have here at Penn State, in order to come up with simulations. And when we compare it with ERA 5, we call it ground truth. It's not exactly ground truth, but we are using ERA 5 analysis to train our model, and then we use the system to forecasting. And this is in the case of a hurricane, how this is ECMWF that is considered one of the best models. It didn't do very well. This is for a typhoon. And whereas Pangu weather almost cracked the ground truth. So I was able to outperform the best physics-based system in the world. This is the Stormer project, which is let me see if I can show you this. So this is again initialized with ERA 5, and we are able to really get the purely learned model. You can really get the down to learning the physics. And in fact, I just want to show you this. This is the initial conditions in which we are able to simulate very precisely this was a 5-day prediction for a cyclone happening here in the Pacific. So again, in case of an extreme event, and here we are, with 2019 all the way to 2025 was last year. And this is the skill, basically the ability to do good predictions. You can see that, all those are AI-based system, and then, everyone is converging right here, where what does it mean 125%? It means that it's outperforming the base, which is ACMWF, the best physics-based system. So, and this is the one that, we are working on here at Penn State. So we are doing extremely well and on par with much larger groups than us. So why is that important to have this? Well, now that, we can perform a simulation, it is still one case. We still want to be able, to come up with a probability of possible outcomes. And this is a methodology that has been developed at NCAR, and I've been working with colleagues at NCAR for quite a few years. It's called analog ensemble. And the idea is that to generate probabilistic forecasts using a single deterministic forecast, a set of historical forecasts, and associated observations. So we know so for every past forecast, we know what really happened. So the idea is that, well, because, those models are deterministic, if they made an error in the past, they're still going to make the same error, assuming there is not an update in the model. So it's very highly dimensional. When we talk about similar, what does it mean to be similar? Well, we have, thousands, hundreds of thousands of grades. We have hundreds of parameters. We have usually just a handful of this. Sometimes we go to 48 hours every hour. So this is about the smallest term. It's only about in the 40s, with this in the hundreds, and this potentially in the thousands. An historical forecast, same dimension plus days. Sometimes we use 10 years. So it's quite a large number here. Whereas the observation, of course, they're just have, the observation, the parameters, and when they were made. Usually the observation have a much finer temporal resolution than the lead times, which is every hour or every 3 hours. So NCAR did a lot of work using this analog. Is shown to be working really well, but this similarity is very difficult. For the most part, they use an Euclidean distance in this multidimensional space. What we try to do is just to transform this space into a new space where this transformation is performed using a neural network. We use a triplet network training. So for an anchor, so this is a forecast. Then, we pick up two. One that we know that is more similar, and this is based on some outcomes of that particular forecast, and one that is negative, so that, it's not as similar. And we do this, thousands and thousands of times for, hundreds of predictors. And over time, we learn basically a similarity, this concept of similarity. For this particular setup, we use NAM, 8 years of training, 1 year of testing. We use, using the analog, only 5 predictors, because, the analog becomes intractable with more. Whereas with the deep analog, we use all 383 atmospheric variables from multiple vertical layers in our NAM project. And here, just, those are violin plots. What we have here on the vertical axis is solar irradiance. This was a project for renewable energy for photovoltaic. So we're trying to predict irradiance using, and we are comparing with surf-rad. So this is real observations. This is using NAM, using the traditional analog. This is using an optimized version of the analog that is very computationally expensive. And this is using our deep version of the analogs that works extremely lean in computational sources. And here we're showing you all the points where we computed. So the spatial consistency is very high. Red are the stations where the model was not statistically significant, and green where it was statistically significant. And and the green one, the thick green one, statistically significant, and the light green ones, it was just an improvement. And then, these are something that I wanted to show you. So this is, as you can see, is solar irradiance. So, we have the peak is the solar variation for different predictions. And here, this gray is an area that, we want to identify. So in this particular graph, we're just showing solar irradiance versus relative humidity, for example, two variables. where we have all the forecasts available. We have those are what we, according to the analog ensemble, are the most ideal forecast. And those, the X are the optimal and from the analog, and the pluses are what are the optimal from the deep learning. So when you look at here, it's not entirely clear why the deep learning would be better. But once we look into the latent features, so this is the space that was learned by the deep learning algorithms, then you can see that what you learned was much, much closer to the target forecast. So showing that there is indeed, like an understanding, it was able, to identify the forecasts that are indeed more similar in this multidimensional new transform space. So what we learned, we can use it. The similarity based on latent feature outperforms and is much faster. And we can ingest hundreds of predictors. We no longer have to limit ourselves to a few of them. And these are second examples because, we have done it, spatially, but one grid at a time. How about if we want to keep the spatial consistency, if we want to learn from an entire space? While the original analog just looks one grid at a time, there was one version that, it was taken by considering the nearby grids. But here, what we want to do is really what we call the spatial analog, to look at the entire domain at once, spatial domain. And this is how it works. I'm going to skip over the details, but we give the input, we compress it, we have latent features, and we use num again. This is using 3 years for training, 1 year for testing. And what I want to show you just very, very rapidly, I'm not going to go over all this, but that, with this spatial version of the analog, we were able, to increase the results very rapidly. And what we have here is just one such example. This is our anchor forecast. So this is how it looks. And we're really looking specifically here in central Pennsylvania. And all the best forecasts, they do tend to have, the same spatial patterns over this area. Here we're giving, the top 20 something I've got. So that was good because, by encoding space, we can keep spatial and temporal information. And we seem to have a better continuity. And, this is a speculation, but the intuition is that it is more consistent with physical error process. We know that on the Earth, then, we do not have sharp discontinuities for the most part in fields that we know to be continuous. And by learning them all at the same time, we ensure that this continuity is kept. Okay, so for the last 5 minutes, I really have only 5 minutes, 10 minutes maybe. Then I will take questions. I want to talk to you a little bit about, spatial algorithms. So we've seen that these AI and machine learning are very powerful algorithms, but they're often not the best way to solve a problem. I sometimes tell my students that, AI are the second best way to solve a problem. There may be more accurate and environmentally friendly solutions out there. And something that I do and encourage you to do the same. When my students publish an article like in the acknowledgement, I ask them to estimate what was the carbon footprint of the simulations that they were performed. And why is this important? So this is what I know from OpenAI. We're talking about GPT-3, now we are Model 5. But their earlier version that is very similar, a little bit smaller, they use 512 V100 GPUs over 9 days. Each GPU used between 200 and 300 watts. So what that means that just to train one version of an old model, we use about almost 30,000 kilowatts hours. So given that average household here in the US use 10,000 kilowatt hours just to train one instance of a model, use enough energy as 3 American homes. So it is becoming a thing. You see, Earth system modeling must become more energy efficient. This is back in 2020, we were talking about this before this rapid increase in AI. Modern society is very good at obscuring environmental impacts. Projection indicated by 2030, energy used by communication technology will contribute to 23% of global greenhouse. Energy consumption of AI pose environmental problem. This is back in 2021. This is, it's a problem that we have speculated and now we are seeing. And, I'm going to skip a little bit ahead. But what I wanted to show you is that, only basically the AI part of Google use entire country of Eritrea. Now, Eritrea probably you don't think of it as being, a very power-hungry country. It is a country of 4 million people. So right now, the footprint of AI for 1 year of one company, just AI is enough as millions of people. So what are we trying to do here at Penn State? And we're trying to work on this, is what we call this frontier project. So we're trying to acquire a small micronuclear reactor in the 10 to 15 megawatts, and to co-locate all our AI system in the same location as we have this nuclear reactor, so that we can power our system, with a zero carbon emission energy. And the reason why this is important is because, if you think about climate change, right now we're using AI for climate simulation to the point that, the simulation itself on what is the cost of carbon on climate is by itself responsible a little bit, for this increase in carbon consumption. So that is clearly not sustainable. Some conclusions. So here we've seen how AI opens incredible opportunities for our science, and I gave you a little bit of like a part related to remote sensing and numerical modeling. We're seeing this acceleration of rates of discovery, and but do please keep in mind that AI might be the second best way to solve a problem, and there may be more computational and energy efficient algorithms out there. And with this, I am done, and I will take some questions for you. And I kept it to 30 minutes because I knew that, as Zoom,
Thank you
I didn't want to overwhelm with too
for
much presentation.
time for discussion as well. Thank you, Guido.
Thank you.
So we have, geography departments are very eclectic, with people from the physical side, technical side, but also we have human geographers here. So you may get some questions in that frame. Maybe I can just start off with one. You mentioned the issue of energy usage for AI. I feel that is very well studied, and the greenhouse carbon footprint aspect is often used as the key metric. My concern is what we are missing, the elephant in the room, is the material needs of AI. And especially being based in a mineral engineering college, I am alarmed by how little data we actually have on the material needs of AI, the infrastructure, the chips, the gallium for nitride, and all this. And I'm wondering if that has crossed your desk, those kinds of issues as we're doing the sustainability accounting.
Yeah, no, thank you for that. Yeah, you're right. That is not usually talk. We talk about, the end product. Okay, now that we have the computer, how much power it uses. Yeah, in the institute we do have one new initiative, which is, for the critical and strategic minerals, and part of it is indeed related to computing. And the reason is that, yeah, I mean, those elements are needed, but they're not easily recyclable. So, once a computer, it passed its use, there is some level, some recycling, but it's particularly not the gold on the contacts. There is no really any cost-effective way, to recycle. So it's becoming, just an incredible amount of waste of this electronic waste.
And my major concern is there's not even any modeling. I don't know if AI can be actually used to model. If you upscale AI in every sector of human society, how much infrastructure will you need? If you're going to be doing air traffic control, climate modeling, water modeling.
Oh, yeah, yeah.
Yeah,
this is at the current level is unsustainable. So
yeah,
is absolutely unsustainable to the point that each one of us, I don't know if it's Delaware, but here in Pennsylvania, the cost of electricity production went up it doubled actually. It doubled in a year. Now, because the cost of electricity is usually I mean, you have the production and the distribution. Distribution remain constant, but I used to pay about 5 cents a kilowatt hours per production and 5 cents per distribution, so 10 cents total. Now it's 15. So basically, the cost of electricity went up 1/3 because we haven't planned for this. And there is one thing that, one point that I would like to make is that if you look at the United States, all the critical infrastructure that came out of a master plan. There was a master plan for the highway system. There was a master plan for the distribution of electricity and for the water and the sewage in every city. Whereas computing, it did not come out of any master plan. The internet was industry driven. We let Verizon and a few other companies to put the infrastructure, Xfinity, to put the infrastructure to provide the internet without any master plan. We're doing the same mistake again now with AI, in which we have data centers that are really industry driven, and they become very opportunistic, and those are money making, right? I mean, sustainability is not as important as making money, and probably making money in the short term, not in the long term.
Yeah, very good. Well, I'll follow up with you on that. Maybe we can do some publication on that, because my PhD is in planning actually, and I'm a big flag bearer for planning in a geography department. So, all right, let's open it up. Others.
Yeah, I can ask a few questions. Thank you for your presentation. Okay,
Please introduce yourself also, yeah.
Yeah. Hi, I'm Yang Hu, assistant professor in the Department of Geography, also in the Department of Civil Engineering. So I have a few questions actually about the models. One thing you are talking about, to get your opinions on. I see actually you use the deep learning models to make predictions. What are your opinions on actually the model overfitting issue?
Overfitting, you ask me?
Yes.
Yeah, well, that is one, of course, always one of the problems, that we're dealing, with every time you do any AI. I mean, are we really learning, or are we only memorizing? And in the case of weather, the search space, it is so large that we haven't seen that happening when we look for very large data sets and time steps in the past. It is indeed a problem, though. More than overfitting, the problem is that I kind of, I said something before, and nobody picked up on it, but I said, we come up, with physically consistent model. Well, that's not entirely true. So we are seeing models that they show, some dynamic behavior that is consistent with the physics that we know, but they will diverge. They diverge, actually rather rapidly. So I showed you, 1 day of simulations. It will hold for 2 days, maybe we'll go to 3 days, but after 3 days, we see things that they're just not physically consistent. So those patterns that we're learning, we know that they're only good for a short time step. So there is that maybe an overfitting? It could potentially be, because we're just learning those patterns that they're short term. We're not really learning any physics. And there are some attempts in atmospheric numerical models, rather than learning the patterns, to learning the physics themselves, but they tend to not perform as well as those that I showed you, where we are actually trying to make a direct prediction.
Thank you. Actually, I have a follow-up question. So I see actually when you do this, you use a deep learning model to actually quantify uncertainty. So you use 380 plus variables, and then you get the latent features.
Yeah.
So then you claim from your presentation that actually the results are very good. So my question is related to when you actually convert your variables into latent features, how do you think about the interpretability of your results?
Oh, no, 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 thank you. I mean, that's a, thank you. That's an absolute fantastic question. So, what we do, we take those variables, we build, the latent features, and then, of course, we expand it. I mean, the prediction is done in physical variables, not in latent features. Um, you asked me what is the interpretability? Well, I mean, I don't know. What the experiment that I showed you was tried. Well, let me try to visualize, those latent features. They don't really mean much to me. But what I can try to do, I can try to put some anchor points. So I know that this is something good. This is what I'm looking for. Show me how it is in latent features, and it is one point in the space. And then, when I look at what are the most similar ones, if the system has learned, I would assume them, to kind of cluster around it. So, I cannot tell you what it means because I don't know. It's just, some weird variables. But the moment I see that the two concepts that I know in physical space to be close, they're also close in this latent space, then by intuition, I says, well, it must have learned something because the things that tend to converge over an area of the space that I cannot explain to you. I don't know how it looks like. But the fact that things that should be similar in the physical space are also similar in this latent space, it makes me believe that something was learned, some important characteristics were learned. Does it make more sense now?
Yeah, I think that's a really nice actually explanation. If I have time, I want to ask you one more question. So, you're talking, so deep learning models are very data intensive. And when we want to use this kind of model to predict extreme events, for most cases, we don't have enough data actually for actually extreme events. What is your opinion to use deep learning models for extreme event prediction?
Yeah, right. I'm totally with you on that. What we were showing here is that even for extreme events, those patterns, they were working. I mean, I'm not coming here to claim that our system will get every extreme event, but it did get, the cyclone well. Why is this important? I want to give you like a little bit of my own personal experience. And that goes back, to when I met Christina, like, over a decade ago that we were at NCAR. Back then I was really proposing AI and computing, and many of the colleagues at NCAR, they were saying, "Oh, this will never work." I mean, it really was a brick wall. It was like, "Oh, no, 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 we need to get a better physics. We need to go and make better field studies to understand, better." Cloud physics so that we can code it into the model. But as I was saying, well, maybe we can use AI. Then, you fast forward a few years and we start seeing especially Pangu weather. And many of the colleagues back then were saying, well, this is only going to work for, the vanilla case over, very global model. It's never going to work for hazards. And then, we start showing, no, no, it does work. And then, the next criticism was, well, but this is only a global model. It's never going to work for regional model. And there we go. And now that regional models are also outperforming the skill of ECNWF. Not all the time, but in enough cases that there is research being directed there. So what I would say is that there's always been quite a skepticism because it seems incredible that a system that is data-based will be able to determine something that is rare in the data, something that he has never seen before. But if you think a little bit about it, even extreme events in weather forecasting, they're patterns. They're just rare patterns. But the pattern is there in the data. It just, it's not so explicit. So if the system is truly learning, the basic conditions of the planet, it should be able to even get, those rare events. And I know it's a bold claim, but the idea is that is the system just learning patterns, or is the system really learning, some of the physics behind, some of the dynamics behind? And I think it is. I think, the reason why they're working well, even in data sparse situations, is because, they get the dynamics right. And a lot of the work we're doing right now is through it's basically a dynamic system. We're using a surrogate model to learn a dynamic system.
Thank you.
You're welcome.
Okay, we have a question online from Gabriela,
Sorry, I didn't.
who's an economist. Gabriela, you can unmute.
Thank you. Thank you for your talk. I have a couple questions. In this AI modeling, do you have some kind of a mathematical or statistical methods to to measure how unbiased and how robust are the models? Right.
So
And the second question is, maybe I ask you the same. Also, say that you generate data for, say, mention climate change or
Mhm.
carbon emissions, and I may generate my data and you generate your data. Do you have also, in that sense, some kind of a statistical test to say, well, the data or your data is better than mine for the following reasons, following a statistical theory or statistical method?
Mhm.
Because there will be at some point there will be hundreds of, if not thousands of data on climate change generated by AI models.
Yeah.
That say the scientists, say I don't do that. I don't want to study, simulation of climate change or carbon emissions or whatever.
Mhm.
Which data should I rely? Do I follow some statistical test? In short, my question is the mathematical strictness of testing the AI models, and then how to test the quality of the data.
Okay. Hope to remember all the points. So let's start a little bit by saying that for weather, I'm first going to answer in the weather settings, and then I will answer in the climate settings. So when we talk about weather,
It doesn't have to be the weather in general, which can be,
yeah,
for example, education or
yeah. But let me say one thing that,
Yeah.
in case of weather, we know the truth because, we see, we measure it.
yeah.
As long as the variable is measurable, like we did irradiance in our case, or could be rainfall or temperature and so on, then there are different statistical tests. I can tell you a few that we use because there is not just one single test that can capture all the different variability. Sometimes you care that some values are correct in the right locations. Other times you just care about the distribution because if you think that this a numerical model, a forecast is just like one point in a probability distribution function. If we run the model many times, each time, we will get, by changing the parameter, we'll get, a slightly different value. So we would like to do some, basically not compute point per point, but, to think that is part of a distribution. Now, if we don't know the truth, like in climate, for example, it's very hard for anyone to say, what is the best system, like a AI system versus, the physics-based system, because, you don't know the truth. You can compare over the past, but, we have zero guarantees that the future is going to look anything like the past. As a matter of fact, we believe that you will not. So I don't really know how to answer your question in terms that there is not one equation, one test, or one data set that, is better to do those comparisons. But when enough models that tend to converge towards the solutions, then we increase our confidence. Think about in case of hurricanes, we have those like spaghetti plots, and then we create a cone of uncertainty. That cone of uncertainty tries to depict the uncertainty of multiple models, and each one tells a different story, and then most of them tend to agree over an area, and we believe that's to be the best track, the most likely track. And then, but there is that uncertainty that increases with time.
But regarding modeling,
Mhm.
how do we, how do you choose, how do you know your model, your mathematical model is robust, it's unbiased, and theoretically speaking, you use these algorithms and you have these parameters. So, in mathematics, you
Yep.
you can show, specifically this model is robust and to different setups, right? So
Yep.
do you
So
do that in AI modeling as well?
yeah, so I mean, we start, the input is from a model, right? This era 5 of the NAM, or it is a model for which there are some statistical tests that are performed in order to determine how robust they are. So the input, we have a certain level of uncertainty. Now, when you make the forecast, the question, if you want to know how robust this forecast is, well, it can only be done, as far as I know, I mean, statistically by running the model multiple times and then compare with what we call, the ground truth, which is not the ground truth, but that's the closest thing to the ground truth. And we have, method in order to measure. And sometimes, and what I was saying before, that there is not just one single measurement of robustness. It really depends. And there is an whole set of tests that we perform, CRPS, and that's the first one that comes to my mind. But we do rank histograms. Then we look at, of course, RMSE, even though it's not very indicative, and the bias in the model and so on. And then, based on the different scores and the different conditions, we tend to come up with heuristics that this model seems to be more robust in this part of the year over this part of the world, whereas other models that tend to perform more robust in different parts of the world. But of course, robustness doesn't go hand in hand, with skill often. So that's the way that is usually done, for comparing, learned model with physical models.
Thank you.
You're welcome.
Okay.
Yeah, we have 1 hour.
Any other questions from the room or from online? We have our state climatologist also on the call, Kevin Brinson. So any work they're doing here in terms of the weather prediction, short term versus long term. Kevin, anything you'd like to ask?
I mean, I had more of a philosophical question. I didn't want to open up a can of worms, but
Mhm.
I always think about AI and sort of the black box a little bit, and our need to understand why something is the way it is. Why is a prediction coming out better this way than another way? And I don't mean that just in terms of, the methodological differences, but just even like the physical understanding of it. And I guess my question for you maybe is, how much does that matter? I mean, it sometimes it is important to get the answer right, but it's also nice to know why the answer was right. And so I think sometimes with AI, it's difficult to sort of, I don't know, maybe emphasize that in certain situations. So what's your perspective on understanding why the AI is getting it right?
Yeah, so thank you for the question. So I go back, when I did my PhD back, in the mid 2000s, we were using AI. And at that time, AI was very different than what we have right now, both in capabilities and in methodology. I was working on something called, symbolic rule induction. And the reason why I was doing that, because it was highly interpretable. So I truly believe that, interpretability of results was the only way to really trust an algorithm. That, if we would not be able to inspect and understand what was learned, then, we wouldn't trust it to use it. I mean, remember, the example that I used to give back then was, well, if you go to the hospital and, you put all the input into your AI system and the answer comes, cut your arm, well, you probably want to know why. And I truly believed it. I mean, I would my philosophical answer back then was, well, if we don't understand it, then people won't trust it. I think I was wrong. I mean, the last 5 years that proved me wrong. I mean, there is so much that, we're relying on AI. And it's scary, right? Like face recognition. Police automatically uses face recognition, or even border control, right? So we are letting, algorithms that learn that we believe to be robust based on the previous question. We run some statistics, but we know that they fail. And the problem with AI is that, right now, the system, at least the ones that I know of, when they fail, they do so with an unknown level of uncertainty. So, when it's very hard to predict when they will fail and how they will fail. We just know that they fail in certain conditions. So we basically say, oh, under those conditions, those algorithms will not work, but we don't really know why. So, so I can only, I wish I could tell you, no, if something is not understood, then, it will never be used, but that's not what we're seeing. We're seeing the opposite. Is it dangerous? Absolutely. Does it really increase science? That's a question that I have for myself. I mean, just the fact that something works, the fact that we can do a better prediction of how much snow there is going to be next week, doesn't mean that we improve our understanding of science, our planet, or maybe not. And for some problems, probably matter, some problem not. There was a very nice book I read. Was called An Army of One. And no, or maybe An Army of Zero. I don't remember, but it was a former US military. It was talking about, the autonomous systems in the battlefield. So where we actually use systems that are AI based, they're fully autonomous, and they actually can employ lethal weapons. So let's say that, there is a mistake, and, that, someone gets killed, by mistake. Now, whose fault is it? And he was saying, is the fault of the general that, has come up with a doctrine, or maybe the unit commander that deployed such asset, or maybe the company that built it, or maybe the software engineer that trained it. It is really a philosophical question once we start relying on potentially, life and death decision. That was viewed in a military settings. We can talk about medical settings. We can talk about many different settings.
Yeah, the book is called Army of None,
Army of None. Yeah, that was
Autonomous Weapons and the Future of War by Paul Shard.
Very timely book with some of the recent news.
Exactly. Sadly,
yeah. You know why Army of One was the official motto of the recruiting motto of the U.S. Army. I remember, and he wrote the book Army of None.
Yeah.
Yeah, I mean, again, I'm not really answering your questions other than saying, yeah, I mean, I share your same concern. I believed something when I started it, and now, unfortunately, that belief. I mean, I think, there is this idea of understandability of AI. We're talking about the ethics of using AI solutions that, we do not fully understand. But the point is that, we do. I mean, we ask Alexa, to do things for us, and we trusted that, they will do it well. And, again, I should give you the example on border control. That really bothers me. I know that, we're using, like some systems, right now to make decisions on economic decision, like, do we give loans? Insurance. Right now, AI systems, they're being used in order to set insurance premiums. So maybe, some of us are overpaying and some are underpaying just because, some system we don't fully understand made such a determination. I see Christina coming.
Now I think we're ready to close.
Oh, yeah.
And so are there any more questions? I mean, I would love to talk more philosophical
Yeah.
thoughts about AI, but maybe we should.
Yeah, especially with this Anthropic decision. I think this guy has made a really principled decision, which is he's going to lose hundreds of millions of dollars.
He's Italian.
He's a he's
Anthropic
Italian.
was, we're
Dario, yeah,
Italo Americans, yeah.
Yeah, it was quite remarkable. So
No, it's just that every time I go to talks by computer scientists or people that have already embraced AI,
yeah,
you get this very enthusiastic description, paradigm shift, incredible discovery. And then you go to a whole different community that is like, where exactly is all this improvement? All these bias improvements, RMSE reductions. Sure, there has been a small increase in the performance, but the cost.
Mm.
I mean, do we understand the billions of dollars that have gone into this? Everybody's investing in AI, everybody's using energy for AI. And what at the end of the day, in my life, in everyday things, what has gotten better? A few things. And then I feel like everybody has to use AI as this new toy that everybody wants to use. It's not really that there's a need to use AI, there's a want. Where we have this carrot ahead of us. Oh, we will solve all of our problems. I have not seen that. The latest storm that hit our area was the worst predicted storm in the history of humanity. We were on Friday night, and we still didn't know at what time it was going to snow the day after for the first time with all these AI models. So just like you came up with a million of examples where it outperformed existing situations, I can come up with another million examples where AI sucked. Seriously. And so to me, the real paradigm shift has been from understanding the world to measuring the world and trusting that the data is the solution. Now, if a huge company puts out a sensor that is wrong, and now we have millions of wrong data, nobody in 10 years is going to be able to understand that there was something wrong in the physics because we rely on the data. So there's all these dangers to be ahead of us. And missing a weather forecast, okay, not a big deal. But again, we are in the surgery room. In 10 years, it's going to be a robot that operates my heart. And like the same thing, this robot doesn't know anything about the physics. But our doctors will not know anything about how the earth works, the body works, it will be based on data. And I'm like, this is the real revolution of AI. And as you were saying, do we accept this or not? Sounds to me like it's too late to say no, but it's a very dangerous path. And so I think this will be the challenge of the next 10 years, being able to make a wise decision about where to go.
I think part of it is like when humans are using the data to analyze versus the algorithms, then like, for example, for cancer screening using ultrasound data, like if you're getting a doctor to look at it versus an AI model, the AI model will do better. I mean, there's pretty good evidence. So it's partly that aspect where AI is most
But I'm saying,
useful,
let's say that
right?
there's a pixel that's faulty in the machine. I mean,
But then the humans will make the same mistake. So that's what I'm saying.
Be able to tell. Anyway.
If they're still using the ultrasound, they will make the same mistake, right? So that's the only part where it's useful.
There is another issue also here that the democratization of AI. Who can have access? Not everybody have access to AI data or AI machine.
Yeah,
So
equity issue.
there will be how to democratize that. I don't think anybody has discussed much that, right? So that's a question also.
But it sounds like it's very democratic. I mean, it's pretty widely available.
Yeah.
So,
say farmers, farmers every farmer in developing countries have access to the AI, for example?
Yeah.
Oh,
yeah.
I'm pretty sure farmers are using it.
No, there are evidences that they don't, right? So
Yeah, no, it's still more in the developed world. But yeah, I think one of our faculty, Kyle Davis, he's looking into that in Nigeria actually to see how they can use some of those techniques for irrigation and optimal irrigation, where to put the water and all that. So
we'll see how much better though.
Oh, let's see. But this has been great. Thank you.
Well,
okay, shall we say goodbye then, or
Thank you so much. Yeah,
but it was great. It was really eye-opening.
Stimulated a lot of, and I will follow up with you then, Guido, on an idea to collaborate.
Yeah, I would love so. Thank you so much. I'm sorry I couldn't be there. And
you're back.
Yeah,
but I'll visit again. Fortunately, I visit Christina often. So next time I'm in the department, I'm gonna let Christina know it well in advance. So maybe we get to meet in 3D.
Absolutely.
Yeah,
3D.
Definitely. Send us some good graduate students from your undergrad program. Yeah.
All right.
Yeah.
We'll do that.
Okay.
All right. Goodbye. Thank you again. Thank you again. Grazie, Cristina. Grazie.
Thank you.
Ciao.